Good day, students. Welcome to part 8 of the Integrated Algebra Regents review for January 2014. In this installment, we're going to be going over problems 35 through 37. And don't forget, the other clips can be found at mathgoodserve.com/testprep.html under New York Regents. All right, let's take a look at problem 35. It says Terry estimated the length of the edge of a cube to be 5 centimeters. The actual length of the side is 5.2 centimeters. Find the relative error of the surface area of the cube to the nearest thousandth. Okay, so we have to be careful here to note that we're not looking for the relative error of the measure of the side of the cube, but we're looking for the relative error of the measure of the surface area. Okay, so before we go ahead and calculate that result, let's go over the formula first. The formula for computing the relative error. Okay, so relative error is going to be can be found by determining the absolute value of the measured minus the actual absolute value of that difference divided by the actual, okay, over the actual. So in the context of this problem, what we're going to be looking for is the relative error of the surface area is going to be the absolute value of the measured surface area minus the actual surface area, okay, divided by the actual surface area. So what I'm doing right now is basically applying this general formula up here to this particular situation, which is the surface area. Okay, so what is the surface area of a cube? Let's go ahead and determine that formula also. All right, so let's say we have a cube. So we know that a cube has 6 faces, and the area of each face of the cube can be calculated by multiplying the length times the width, right? So the area of a face of a cube is s squared. So since they have the cube has 6 faces, the surface area of the cube is basically 6s squared. Basically 6 times the 6 square areas of each face of the cube. So this is the formula we're going to be using to calculate the relative error of the surface area. Okay, so looking at this formula we have here, we have to find the measured surface area first. So let's go ahead and find that measured surface area. So we need to use the measured side lengths. Okay, so measured side S is equal to, what did Terry measure? She estimated 5 centimeters, so that's the measured side length. So measured side S is 5. So the measured surface area is going to be 6 s squared, which is going to be 6 times 5 to the second power. And then 5 times 5 is 25, times 6 is 150 centimeters squared. Now, next thing we need is the actual surface area. Okay, actual surface area is dependent on the actual side measure. Okay, so the actual side S is going to be 5.2. Okay, 5.2 centimeters. Let's make sure, because if you look at the problem, it says the actual length of the side is 5.2 centimeters. So that's the actual side length. So the actual surface area of the cube, 6s squared, is going to be 6 times 5.2 squared. All right, and we enter that in our calculator, we'll get 162.24 centimeters squared. Okay, now we have everything we need to calculate the relative surface area. So let's go ahead and compute that. So the relative error, the relative error of Terry's surface area is going to be the absolute value of the measured surface area, which is 150, minus the actual surface area, 162.24. Absolute value of that divided by the actual surface area, which is 162.24. Okay, so let's go ahead and enter that in our calculators. All right, so absolute value, you can find that under catalog. Let's go to second function 0, takes you to catalog. AVS is absolute value. Absolute value of 150 minus 162.24. All right, divided by the actual, which is 162.24. Enter. And your answer is 0.07544. Okay, so the relative error is 0.07544. We are asked to round to what decimal place? If you go back to the problem, we're asked to round to the thousandth. Okay, so where is that? This is the tenth, hundredth, and thousandth. Okay, so this is where we're rounding up to. The number behind is not 5 or greater, so we're going to just truncate that piece out, and our answer is going to be 0.075 to the nearest thousandths. Okay, all right, and now of course the unit is centimeter squared because we're looking for the relative error of the surface area. All right, so that's that. All right, for 36, this is an application of right triangle trigonometry. So let's go ahead and take a look at the question. It says, from the top of an apartment building, the angle of depression to a car parked on the street below is 38 degrees, as shown in the diagram below. The car is parked 80 feet from the base of the building. Find the height of the building to the nearest tenth of a foot. Okay, so this is the situation here. We have a right triangle. This is 90 degrees. We are to find the height of the building, so let's call this x. Okay. In order to use right triangle trig, we need two sides and an angle in order for us to set up the problem. Okay, but if you look at this triangle, we have only two sides. How can we find an angle so that we can set up a ratio? This 38 degrees right here, what does that tell us? That's a very important hint. Now, if you think back to geometry, or if you've taken geometry, this side right here is parallel to this side, so that 38 degrees angle of depression is equal to the angle of elevation from the road to this line of view. Okay, so if that's 38, this right here is 38 degrees also. Okay, now we have a right triangle involving two sides and an angle. So right triangle trig, we should think about SOHCAHTOA. All right, now we are going to be using one ratio here to solve this problem. So is it sine for SO, cosine for CAH, or is it tan for TOA? So what we'll do is we'll label the angles we need, the sides we need, and the sides we know, and that should help us figure it out. Opposite of 90 degrees is the hypotenuse. The hypotenuse is the longest side of the triangle. The side opposite the angle that's given, this side opposite this angle right here, that is known as your opposite. Okay, so this is your opposite. For O, this is H, and then this other side right here is the adjacent. Now, if you examine these three sides, which side do you not know and you do not need? I know this side. I need to find this side. The hypotenuse plays no role in this problem. We don't know it. We don't need it. So we just scratch it out. Okay? So we need the trig ratio that involves opposite and adjacent. So if you look at SOHCAHTOA, which trig ratio has just O and A? It's TOA, right? So what does that tell us? It tells us that tan theta is equal to opposite over adjacent. So you see how that trig ratio relates the side to an angle, two sides to an angle. All right, so let's apply this formula to this situation right here. Theta is the angle, of course, so we have tan of the angle, 38, equals the opposite, which is x, what we're looking for, divided by the adjacent, which is 80. Now to get x isolated, we'll multiply both sides by 80, 80, and 80. And then our final answer, the height of the building x, will be 80 tan 38. Okay, so let's go ahead and calculate what that is. Since we're dealing with degrees, let me make sure my calculator is in degrees. It's not, so let's do that. All right, so let's enter the expression. 80 tan 38. And our answer is 62.502. So the height of the building is 62.5028. But we are to round it to the nearest tenth of a foot. So let's write down what our answer is. We're going to be rounding it up to this tenth right here. The number behind it is not 5 or greater, so we're just going to drop off that piece. So let's write down the answer. The height of the building. The height of the building is 62.5 feet to the nearest tenth. Okay, so that's that. All right, let's take a look at problem 37. It says, on the set of axes below, solve the following system of equations graphically for all values of x and y and state the coordinates of all the solutions. So what we have here is a parabola and a line, and of course they can intersect at most. There can be at most two intersections, one intersection and no intersection here. But if there are any intersections, those would be our solutions. So this is an excellent problem where we can use the graphing calculator, but we also have to clearly illustrate our graph on this grid right here. What I'm going to do is I'm going to start with the easy one first. The easy graph to draw is the line. Y equals 2x plus 3. Now, do you remember the point-slope form of the equation of the line? I'm sorry, the slope-intercept form. Slope-intercept form is y equals mx plus b. And this tells us that m is the rise over run, and b is your what? B is your y-intercept, where the graph starts on the where the graph intersects the y-axis. So in this problem, m is equal to 2 over 1, which means we're going to rise 2 and run 1. Where are we going to start from? We're going to start from the y-intercept b, which is 3. Okay, we can see that b is 3 and m is 2. All right, so let's go ahead and mark 3 on our graph. 1, 2, 3 on the y-axis. That's where you begin. You rise 2, 1, 2, and run 1. All right, so those 2 points define the line. Let's grab some more points for accuracy purposes. Rise 2, run 1. Rise 2, run 1. Okay. Fold 2 back up 1. Fold 2 back up 1. All right, and then just draw a nice line here. I'm going to be graphing this with a graphing calculator momentarily, but this is very easy to draw by hand, so I might as well take advantage of that. But it's a different story, of course, with the parabola, which is a little bit more complicated. Okay, so there goes our line. We have the line drawn. Let's label it. The equation of this line we just drew is y equals 2x plus 3. Okay? All right, next thing we have to draw is the graph of the parabola. Now, had it been we do not have a graphing calculator, there's a little work that has to be done to find the points, the necessary points. We have to find the vertex, the intercepts, the zeros, and then also where it intersects this line. Okay, well, since we can use a calculator, let's take full advantage of that. So let's go ahead and graph this parabola right here. And I will also graph the line, but let's graph the parabola first. So we have, let's go to the graphing menu. We're going to graph x power 2, x raised to the second power plus 4x minus 5. Enter. All right, and then let's graph it. All right, I had a statistical zoom, so zoom 6 will give me the standard graph. All right, so there goes the graph. Now, how do I replicate this nice curve on our coordinate grid right here? How do I replicate it? Well, I need to just find a few points. First point I need to find is the vertex right here. Okay, how can we find that? Well, we can think of that as the minimum, so to speak. How do I know that that's the minimum? Well, this is a upward facing parabola, and this is the lowest point, so we can call that the minimum. Why do I have to know the name? Well, we're going to use a special function in the calculate menu. So go to second function trace. You see that right there, the minimum, that's what we're going to be looking for. So go down to option 3, enter. It asks for the left bound, which is a point to the left of your minimum. Because there could be multiple minimums in this graph, but this has only one minimum, so it's going to be easy. But you might wonder, why do I have to do this? It's because of the possibility of more than one minimum, okay? So go to the left of that minimum, see the cursor highlighting the points. Any point to the left, you press enter. The arrow points to where the minimum is located, and it asks for the right bound, so you move your cursor using the right button to any point to the right of your minimum, press enter. So the two arrows are pointing to where the minimum is located, and it says guess, press enter. Boom, there goes your minimum right there. So it's basically -2 and -9, okay, because this goes on and on forever. So -2 and -9 is where your minimum is. X equals -2, 1, 2, and then 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is just for cosmetic purposes. Now, next set of points we want to draw are the points where the graph intersects the line. So how do we figure that out? Well, we have to graph the line also. Okay, so the line is 2x plus 3. 2x plus 3. Enter. Let's go ahead and graph it. Okay, and another thing you also want to note is that at 1 and 1, 2, 3, 4, 5, 1 and -5, we have the zeros. So we can also graph that. That's not really critical, but it's good to take advantage of that. We have a point here at 1 and 1, 2, 3, 4, 5. Okay, but the most important points that we must graph are the intersection points. If you want to get full credit, you must clearly state where those intersection points are on the two graphs. Okay, so pay close attention to this. We're going to calculate, second function calculate, intersect, option number 5. It's gonna ask you for the first curve and then the second curve. The reason it does that is because you could have more than 2 curves here, but we have only 2, so there you have it. All right, so let me do something again. So one thing you want to note is that when you're doing when you're calculating the intersections, calculate intersect. Since there are 2 intersections here, you basically move your cursor to the a point close to the intersection that you want to calculate. Okay, so let's say we want to calculate that intersection first. So when it says first curve, you move your cursor to where to somewhere close to where the intersection you want to calculate is located. Press enter. And then it says second curve, make sure your cursor is close to where the intersection is. Press enter, it says guess. Press enter, and you can see it's 2, 7. 2, 7 is the second intersection. So let's go ahead and indicate that on our graph. So it goes through 2 and 1, 2, 3, 4, 5, 6, 7. Right there. Let me graph these points in green so that they stand out. So we have a point here, a point here, a point here, and a point here. So this is one solution, 2, 7. That's important. You must state the point of intersection. The next one is going to be somewhere here. Let's go ahead and figure out what that is. So second function, calculate again, intersection, option 5. First curve, please move your cursor to a point close to where the intersection point that you want to calculate is located. Right there. Press enter. Second curve, enter. Guess. The second intersection is at -4 and -5. Okay, so let's go ahead and graph that. -4, 1, 2, 3, 4. -5, 1, 2, 3, 4, 5. Right there. So you see the points that define our parabola? You should see it, so let's go ahead and connect the dots. So this is the parabola right here, goes through there, and then through that. Oh, this looks terrible. Through there like that, and then the other one goes something like this through that point. If you do this by hand, it should look much better than this, what I'm doing right here. Okay, so this is basically what it looks like, and we must indicate where the second point of intersection is, which is at, remember, it's -4, comma, -5. All right, so it says we should state the coordinates of our solution. So let's go ahead and state the coordinates of our solution. So right, it's on the side, the coordinates of the solution. Solutions to what are we solving? Systems of equations to the system of equations are -4, -5. That's the first point of intersection, and 2, 7. Okay, so you don't just graph it, you must clearly state what the solutions are. It basically indicates that you understand what you're doing. Okay, and then we have to remember that this blue line right here, the equation of this line is y equals x squared plus 4x minus 5. Actually, on the line of this curve, it's x squared plus 4x minus 5. All right, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel for updates to other cool clips such as this. And do post a comment to let us know what you think about this clip. We really appreciate it. More clips can be found on mathgotserved.com/testprep. Thanks again for watching and have a wonderful day.